but today's lecture is going to be on binary, hexadecimal, and decimal, and the conversions between them, as well as the ASCII table. So by the end of this, you'll be able to take, well, not necessarily an oscope, but later on we'll look at serial communications through an oscope. But you'll be able to take a binary word, an 8-bit word, or a byte, and convert it into an ASCII character, a letter. Also, there's going to be, at the end of this, there's going to be some bonus footage. After the binary to hexadecimal to decimal conversions, and we'll look at the ASCII table too, like I mentioned. Since I do networking for a living and a network engineer, we will take this one step further if you're interested. For those who are interested, I'll include it towards the end of the video. And what we're going to do is I'm going to show you how an IP address is broken down, what a subnet mask is, what your gateway is, and just explain what you see when you do an IP config in a DOS box. So you'll be able to understand the IP address better, what portion is network, what portion is node or host. And then after that, there's, let's call it double bonus time. Larry asked, how do you test an NPN and a PNP? And although it's not going to be a lab, I will show you how to test an NPN and a PNP, how to test a transistor to see if it's functioning or not. And I'm going to take you through a lecture on how to do that, and it's fairly simple, so you'll be able to do it. It just involves the diode testing center on your multimeter, and we'll look at that as well. But right now, let's get into binary. Okay, we all understand what decimal is. We all understand what numbers are, let's say. And today we're going to be dealing with numbers from 0 to 255. So we're going to use an 8-bit binary word. I should probably increase that a little bit. So from 0 to 255. So what is binary? Well, binary is ones and zeros. You can think of them as on-off switches is what binary is. So you only have two characters in binary. You have a 0 and you have a 1 in binary. And hexadecimal, that's actually, so this is base 2. And okay, so this is base 2. Well, and that's from 0 to 1. So from 0, now hex, binary, hex is from 0 to F, and that is base 16. And of course our normal decimal system is 0 to 9, and it is base 10. Okay, so first binary should be the easiest. It's either a 0 or a 1. Now, most of what you're going to see in electronics, the largest you're going to see in binary for what's called a word is 8 bits. So, and that's from 0 to 255. Some of these ICs we'll get into are only 4 bits, but if you can understand 8 bits, you'll understand 4 bits, especially when we do the conversions. So it's pretty easy. So what happens is, in these 8 bits, 2, 3, 4, 5, 6, 7, 8. Each one of these represents a number, and it starts at 1, 2, 4, 8, 16, 32, 64, and you probably notice a pattern here. It just keeps doubling. So each one of these on-off switches represents a different number. And if that switch is on, if that is a 1, then you will add that number to get your total. So here, this total, since they're all 1s, equals 255. So let's take another a number. And let's take the binary first, and then we'll do regular numbers and then turn them into binary. But let's just do 0, 0, 1, 1, 1, 0, 1, 0. Now, of course, feel free to break out your calculator if you'd like. And so what we do is we add up the ones. So here we got 32 and 16 and 8, and the 4 is a 0, so we're not counting that. 2, and then that equals 58. Okay, so we can see now we'll do one more of these. So we have these numbers above it, and once again we can break out the calculator. It's very easily. It's 128 plus 64 plus 1, 193. Okay, so you see how easy it is to take these 8 bits and figure out what number it is. 193. Okay, now how about if we take a number and turn it into binary? Well, that's easy too. Let's take let's see, something higher. Let's take number 246 equals in binary. Now remember, we've got 128, 64, 32. Now we're going in half. 16, 8, 4, 2, and 1. And you can make any number from 0 to 255s. All zeros is 0. All ones is 255. So basically, all you need to do for this is start with 246. Start with your number, and is it divisible by, or can you subtract, let's clear this. So start with 246. Can you subtract 128 from 246? Not is it divisible, sorry about that. And without being less than 0, and yes you can. So I don't know if I hit the minus already. 128 equals 118. So yes, so that's a 1. Now come back here. And can you subtract 64 from 118? Well, yes you can. So we will minus 64. And there's another 1. Now 32. Well, yes you can again. And we'll do a couple of these. So minus 32. So there's another 1. 22. Can you subtract 16 and it still be 0 or greater? Yes, you can. So let's subtract 16. And we add another 1 here. Okay, now 8. Well, 6 minus 8 is negative 2, so no. Well, no, we can't. That's actually a 0. Because if we did minus 8 equals, you see it's negative 2, and you can't have a negative number. So we have 6, so that is a 0. And can we subtract 4? Yes, we can take away 4. And that leaves us, so that there's a 1. And how about 2? Well, yes, of course. 2 minus 2 is 0. See, now that's my point. You know, if it equals 0, that's fine. It can't equal less than 0. So, yes, we have a 1 there. And, of course, 2 minus 2 is 0. Equals 0. And now we're at 0. So you can't subtract 1 from that, so that's a 0. So 246 is 1, 1, 1, 1, 0, 1, 1, 0 in binary. So that is number 246. Okay, let's take another number in binary. Now, if we were just doing 4 bits, we're actually going to be using shift registers eventually. Like I said on the Arduino, we have some digital pins, and you can get an Arduino Mega and you can control, 54 digital pins, and so you can control 54 individual LED lights. We're going to have a lot of projects using some LEDs, but we don't want to use all our digital pins to control them. So we're going to use something called shift registers. And these usually work on binary. So we'll actually get into that. And they usually work on 4 bits. 1, 2, 4, and 8. And of course, if you add up all these numbers together, you have 12, and 3 is 15. 8 plus 4 plus 2 plus 1 equals 15. So if you're only using 4 bits, you have 0 to 15. But right now we're using 8. Most common, especially in communications, when we start developing our own serial communications protocols, we're going to want to use 8 bits. And it's with the standard N81. And we already had a little bit of serial communications when we chose 9600 as our speed. But anyways, let's not get off track here. Let's go back here. Okay, so let's choose another number, and let's make it an odd number this time. We'll use 173 equals. Okay, so we have 173. And yes, we could subtract 128 from that. Equals 45. So yes, we put a 1 in here for that. Now, okay, we can't subtract 64 from 45, so that's a 0. Now 32, we can subtract 32 from 45, so we say minus 32 equals 13, so that is a 1. Now, of course, 16, we can't subtract 16 from that, so that's a 0. And 8, yes, we can subtract 8 from that. So minus 8 equals 5. Whoops. Sorry about that. Let's do plus. Oh, clear it. So that was 13 minus 8 equals 5. So yes, we can put, so we have a 1 there. Now we have 5 left. Actually, I should have done this initially. Just to make it easier, I don't have to be popping back and forth here. Okay, so we have 5, so yeah, 4 minus 5 is 1, so yeah, we can have another 1 here. Minus 4 equals, and then we have 1 left over, so 2 is no, 1 is there. So to say 173 in binary, it is 1 0 1 0 1 1 0 1. It's pretty easy, pretty straightforward. And let's just do one more, and we'll do 17. And then we're going to do our conversions, of course, with hex. And decimal. Right now we're converting between base 10 and base 2 is what we're converting between right now. So let's take a nice low number, 17. So 128, no. 64, no. 32, no. 16, yes. There's 1 with 1 left over. So 8, no. 4, no. 2, no. 1, yes. So that's how you say 17 in binary. Okay, so we've got our binary. Now what about our hexadecimal? Okay, let's take one of these numbers, and they're very easy to turn. Once you have the binary, to go from binary to hexadecimal is very easy. Okay, so we had base 2. So we understand base 10. We work with that every day, 0 through 9. And then, of course, there's 10, 11, 12. So that's base 10. So we have 10 numbers that we're dealing with. And they keep rotating above that. Here we only have 2 numbers. It's very easy. Now base 16 seems a little difficult because we don't have numbers above 9. So what do we do for base 16? Well, they go through the standard 9 numbers first, which is 0, 1, 2, 3, 4, and maybe I should put commas here, 5, 6, 7, 8, 9, A, you don't put 10, it's a single digit, A, B, C, D, E, F. So we have 16 characters here, 0 through F. F being 15, E 14, D 13, C 12, B 11, A 10, and then 9, 8, 7, 6. So these are our decimal characters. So when we have, there are ways to take this number and turn it into this number. But the easiest way to get this number is to go from binary to that number. So hexadecimal, 8 bits in hexadecimal is shown by 2 characters. So you will have 2 characters representing these 8 bits. So let's take 246. So we want to convert 246 into hexadecimal. Well, let's take the binary version of 246, which is 1, 1, 1, 1, and then 0, 1, 1, 0. So the first thing we're going to do is we're going to cut this in half. So now, instead of dealing with 128, 64, 32, 16, 8, 4, 2, 1, what we're going to deal with here is we're going to deal with 1, 2, 4, 8. 1, 2, 4, 8. So each one of these now, instead of representing something from 1 to 128, it actually represents 1. So remember, when I said we had half these characters, you can go from, so we got 8, which is 12, 12 and 2 is 14, so you got 15. So including 0, so you got 0 to 15, which is 16 characters. So each one of these represents 16 characters, our base 16. So each 4 of these represents that. So to say 246 in hexadecimal, well, we have to add these together. So do we count 8? No, 8 is a 0. 4, actually, let's go back to this. Let's bring up our calculator again. By the way, I have buttons on my keyboard. That's how I bring up the calculator so fast. Now, this is simple math. We really don't need the calculator for it. So we're not going to use it. We won't. So maybe we'll use it here. I don't know. So we have 4. So 4, yes. And we have another one here, which is 2. And do we have another one here? No, that's a 0. So 4 plus 2 is 6. So in our hexadecimal, the first character we have is a 6. So, and this is, we're going to do some more hexadecimal because this can get confusing. I'm going to try to keep it as simple as possible. Now, over on this side, we have 8 is a 1, so we want that. 8 plus 4 is a 1, we want that. 4 plus 2 is a 1, so we want that. plus, and then 1 is a 1, so we want that. So this side of 246 is 8 plus 4 plus 2 plus 1, which we know is 15. So, but what is 15? Well, let's go back up here. Actually, snap. Okay, so we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. F. So, to say 246 in hexadecimal, we say F6. Seems pretty straightforward, right? F6 equals 246 in hexadecimal. And to convert backwards, actually, let's do some more conversions. I wish I had a bigger eraser. I gotta get a better program. I'm just using Windows Paint, but we could do it here. Okay, let me get my eraser, or actually, you know what? Let's just choose this color. Choose a bigger line size, and oh, it looks like I got the eraser. Oh. Oh yeah, this is like watching paint dry. So I'll do the magic of video so you guys don't have to see this. Okay, now here's where it can get a little confusing with hexadecimal. We're actually going to do 129. So let's do a little more magic. Let's get rid of 58 here. Depending on how long this is, I might just leave that in there. Paint. Wrong color. Okay, so let's do in binary. Let's do 129. So 129 in binary. Okay, so does 128 go into 129? Yes, it goes in one time with a remainder of 1. So 64, no, it's got a remainder of 1. So this is a nice easy one. And I've chosen this on purpose for two reasons. One, it's nice and easy to figure out into binary. And remember I was saying whether you could subtract it or not? A lot of people, when they figure out binary, decimal to binary, they say, does this number go into this number? And then they have a remainder. So you could do a division instead of subtraction. And that's the more common way, is doing it division instead of subtraction. Let's see. Okay, so we have 129. So 129 in binary is 1 0 0 0 0 0 0 1. Okay, now remember, this is 1 2 4 8. 1 2 4 8. So is there a 1 here? Yes. 2? No. So you would add these. So this equals 1 plus itself, plus nothing, is 1. Over here, this is 8. So we have 8. We have a 4? No. A 2? No. A 1? No. So it's 8. 8. And there's nothing adding, so it's just 8. So how do we say 129 in hexadecimal? Well, we say it 81. So F6 equals 246. But 81 in hex equals 129. Sorry about that. Let's see, 129. So 81 in hex equals 129. See, that's where it can be confusing. So let's actually do a conversion the other way. Let's take a hex number, and figure out what it is, and go through the whole conversion process that way. Okay. We are going to take, I might just do it over here. Let's go backwards. Okay. We're cooking with gas now. Let's take B9. Okay, so we see B9 in hexadecimal, and it would probably look like this. Let's say it's part of a MAC address or something. B9, 86, A2, 97, 63, FF. And say, so we've got this B9. Well, what is this B9? Well, B is what up here? So we've got 0 through 9, then we've got 10, 11, 12, 13, 14, 15. So just so you know what these are, and I'm probably... okay, so this is 10, comma, 11, 12, 13, 14, 15. So B is 11. Okay, once again, is 11 divisible by 8? Yes, it's divisible by 8. There's our 1. How many is left over? Is 3. Is 3 divisible by 4? No. There's a 0. Is 3 divisible by 2? Yes. 1 with 1 left over. Is 1 divisible by 1? Yes. So B is represented as 1, 0, 1, 1. Or it's 11, so we have 8, 9, 10, 11. And let's actually, we'll do that too. And we'll do another one of these as well, or maybe even 2 more. Okay. So 8 plus 2 plus 1 equals 11. 11 is B. Over here, 9. Is 9 divisible by 8? Yes, 1. With 1 left over. Does 1 go into 4? Does 4 go into 1? No. Does 4 go into 2? 1 go into 2 go into 1? Now I'm getting confused. No, there's 1 left over, so there it is there. So that would be 8 plus 1 equals 9. So B9 is 1, 0, 1, 1, 1, 0, 0, 1. Okay, so now we take this whole number here, and let's actually put it up here. There are formulas to do this, guys, and we're not going over the formulas today. We're doing the easy way. You know, someday maybe I'll go over the formulas. I did for resistors in parallel. Okay. So now let's bring this up here. So B9 in decimal is 1011, 1001. So we want to do 1, 0, 1, 1, 1, 0, 0, 1. So now we want to find out what that equals. So let's break out the calculator. So we have 128, yes, plus. We have 64, no. We have 32, yes. We have 16, yes. We have 8. Remember, this is the number that we're doing right here. This guy right here. Don't get confused with the one below it. So, 16, yes. 8, yes. Did I hit that 8? 8, yes. 4, no. 2, no. 1, yes. 185. So, B9 in hex equals 101110001 in binary, which equals 185 in our current decimal system. So, in our base 10 numbering system. So B9 equals this, which equals this. And you know what? I think we'll do another one, just to make sure you guys have it. I know I can be confusing at times, but so we will do another one. Now, if you do enough of these, you start to do them in your head, but you're not going to do a lot of them in electronics. You're going to do it when you're dealing with chips and communications. We haven't even converted to ASCII, so that's our next thing. ASCII is very easy. We just look it up on a table, and we'll do that. So we'll keep this one here. And we'll do this next one, 86. Okay, let's fill this in now. Okay, so B9, so the next thing we're going to do, I don't know if you catch that right, it works out good. Okay, okay, the next one we're doing is 86. So now we're going to do 86. So let's put our 86 right here. 86 equals what? Well, is 8 divisible by 8? Yes, once, with a remainder of 0. So guess what? Ooh, that one's easy. Does 6 go into 8? No, that's a 0. 6 go into 4? Yes, once, with a remainder of 2. 2 go into 2? Yes, once, with a remainder of 0. So, 86 equals 1000110 in binary. Decimal. Okay, so it equals 1000011. Once again, we have 1000110. Okay, break out the calculator. We've got 128 plus 4. Remember, we're not adding 32. That's a 0. Plus 4 plus 2, 134. So 86 in hexadecimal, remember it's a base 16. 86 equals 134. 134. So you got B9 in hex, B9 in binary, B9 in decimal. 86 in hex, 86 in binary, 86 in decimal. And you can convert back and forth using this very easy to use way to convert. Now, what does this mean in ASCII? What is ASCII? Okay, now we'll go to the mouse and we'll go to the internet. ASCII table. And you got complete and extended. Let's go extended. Extended ASCII table images. Sure, why not? I got a couple of these in books, so. Okay, an ASCII table is basically a standard that is used to convert. Now, what a computer sees. This is what a computer sees. It sees ones and zeros. Well, how does it display what we see? It needs to translate this into this, and then translate that into a letter. So, what are our two? What are the twos? We have B9 and 86, or we have 185 and 134. So 185 is actually not on here, and neither is 134. Those are extended. So we could see. Let's go back here. What else do we have on here? We have anything lower? 134, 17. 17 on our ASCII chart is device control 1. So, but you'll see the numbers. 35 in hex. So we have decimal is 53. Hex is 35 equals 5. So if we go to 35 in decimal, it's 23 in hex, and it equals the pound character. And like I said, these aren't scripted. Now you can tell because I didn't choose numbers that fit into the ASCII code. But we've got 134. That's just a little too high. But let's take one of these guys. Let's take the pound sign. 35 is actually 23 in hex. Let's verify that. Okay, so we're going to take, actually let's take something that equals a letter. Let's do 84. So 84 in decimal, according to this chart, it equals 54 in hexadecimal, which equals the letter T. So we're going to start at 84. So let's go back here. And where is our writing implement? There we go. Okay, so we're starting with 84. Now, how do we say 84 in binary? Well, we do our goes into. And 84, nope. 128. 64, yes. With a remainder of what? 20. So 32, no. 16, yes. With a remainder of 4. 8, no. 4, yes. And then 0, 0. There's no remainder after that. So I didn't break out the calculator for that. Sorry, guys. You can do that if you want. Does 128 go into 84? Goes into's. No. Does 64? Yes. It goes into 84 once with a remainder of 20. 32 go into 20? No. 16 go into 20? Yes. 1 with a remainder of 4. 8 go into 4? No. 4 go into 4? Yes. 1 with a remainder of 0. And then 0, and then 0. So now we have 0, 1, 0, 1, 0, 1, 0, 0. Okay? So that is, this is 4 plus 1. 4 plus 1, which equals 5. And over here is 4. and there's nothing to add. So that in hexadecimal, it's 54. So we've got 54 in hex, which equals 0, 1, 0, 1, 0, 1, 0, 0 in binary, which equals 84 in decimal. Now if we come back here, so 84 equals 54 in hex, so we showed that the formula works, and the character is a T. So if we come back here, which equals the letter T in the ASCII character list. Now, you can find these anywhere. It's ASCII. So you can find these anywhere online. You saw how many I found. Let's see if we got an extended. Boom. What do we got here? Nope, just a 127. Let's go back. Extended. ASCIIcode.com. Printable characters. And here's our extended characters. So, let's go back here. We've got B9 and 86, or 185 and 134. You notice they give you the decimal here. They give you the decimal, the number, the hex, the binary, the symbol. So they give you pretty much everything. So once again, we're going. So we'll go B9 and 86. We want to know what B9, so we go by the hex. So we're going all the way down to B9. And see, here's the binary for B9. Let's check that out. 10111 001. 10111 001. And it's this little weird character that looks like a tiny little 1. I have no idea what that tiny little character is. If you know, good for you. It looks like a little 1 or something like that. And 86. Let's go back. And in hex, we've got 86. 86 equals 1, 0, 0, 0, 0, 1, 1, 0. Let's check that out first. Our 86 is 1, 0, 0, 0, 0, 1, 1. 86, that's fine. 86 is 1, 0, 0, 1, 1, 0. And it is a little cross that says it's a dagger. So let's go do that here. And it's almost like our letter T. Okay, I had a brief interruption there, so but I think that just about does it for the conversions. Hopefully you guys understand now what binary is and what hex is, and now we're going to get into IP addressing. Actually, you know what? I should probably... No, I think it's the same train of thought, and then we'll do the PNP and the NPN. Okay, let's open this baby up. We do IP config /all. And I shouldn't have an IP address. No, I don't. Here is my MAC address. This is my physical address. Notice it is hexadecimal. And now you know what you can do in hexadecimal. Usually Microsoft will give you an address if you don't have one. I really kind of wanted to go through this, but I don't want to give out my public IP address. Okay. Let's do it here. Let's start this over again. We'll do it the easy way this time. New. No, we don't have to save that. Let's take a lighter gray this time. You open up a DOS box, and you would type in IP, all one word, config /all. There's no space here. There is a space here. So ipconfig /all. You'll get your MAC address, which you know is hexadecimal now. You'll get your IP address. And we're just going to make one up. We're going to take one from, most people with these wireless routers, they have non-routable addresses on them. 192.168 1.1 is you'll see an IP address like that. That'll actually be your gateway. So your IP address might be 192.168.1.103. And then your subnet mask might be 255.255.255.0. And that, what the mask does, so this is your gateway. This is your IP. And this is your mask. What your mask does is it tells the computer which portion of this IP address is the network, in this case it's this, and which portion is the host. So basically, in your gateway, this is your network, and this is the IP address of the router, or the gateway. So if you remember, we have 1, 2, 3, 4, 5, 6, 7, 8. And it's 128, 64, 32, 16, 8, 4, 2, 1. And remember, altogether that equals 255. So the mask is this whole thing. Each one of these things is an octet. So this says that this whole octet belongs to that. Now, I'm not going to do individual subnet masking. We could have a mask of like 248 here, .0. And then a portion of this is the network. A portion of this number is the network, and a portion of it is the host. But, and if you guys want me to do it, I will. I'll do it in another video. I'll put it at the end of another video. But what happens, so your subnet mask, 255, 255, 255, is all ones. So all the ones are the network, and all the zeros are the nodes. So this last octet, 0, is all 0, 0, 0, 0, 0, 0, 0. Now, your IP address in binary, well, 192. Let's break out the calculator. It's just going to make it a little easier. And I'll move this over, bring this up, max it out in that direction. Where's the calculator button? Right here. Okay, so 192, 128 is divisible, 192 divisible by 128, yes, 1. With how much left over? 192 minus 128 equals 64. And so 64 goes into 64 once with the remainder of 0. So your IP address is going to be 11000000 dot. Now 168. Okay, 128, yes. So 168 minus 128 equals 40 left over. So 0, and there's 1, so 40, and then 2 left over. 2. So your second digit is 1, 0, 1, 0, 0, 0, 1, 0. And the next digit is a 1. Well, that's easy. 1, 2, 3, 4, 5, 6, 7, 8. And that's the gateway. But this is 103. We want the IP address. So the IP address is 103. So 168? No. But 103 minus 64 equals 39. So 1, and it's 39. So 32 minus 39. So yes. And how much is left over? 2 minus 9 is 7. So that's a 0. That's a 0. 4. Yep. So that's 3 left over. Okay, so that equals 103. So your IP address is 0, 1, 1, 0, 0, 1, 1, 1. So this is your IP address in binary. Now what happens is you take the subnet mask, and now we do 255, which is all of this. So that's everywhere where there's a 1 is the network. And 255, and it would be another 255. Let's actually make this 248. It may be a little more complex, but okay, so 248. Yeah, so 248 minus 128 equals 120. So there's 120 left over. Minus 64. 64 equals 56. So that's 32. Wait a minute here. Start over. 248 minus 128 minus 64 minus 32. So we're down to 24. So 16, yes. Minus 16 equals 8. So 16, yes. 8, yes. And then that's it. Remainder of zeros. So in this case, with a 248 mask, we've got 1, 1, 1, 1. And then one more, and then 0, 0, 0, and then the last one is 0. So we've got 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 0. So what this tells us is right here, this dividing line right here, this is what bits are the network and what bits are the node. So this one's easy because it's .1. But let's say we have a more complex address. Let's say it is 129 here. Instead of 1 for the second octet, we have 129. Well, that would be a 1 here and then a 1 here. So our address would read 192.168.129.103. Well, actually, that bit, so our network is 192.168.128 because we only add these bits, and they keep the same number, so it's still 128, 64, 32, 16, 8, 4, 2, 1. Not like when we did remember when we did hex, it was 1248, 1248. Well, here it's not 124 and then 124 over again. It keeps all these numbers the same. All these numbers are the same. So our network is actually 128. And we know that from the mask. We know what bits belong to the network. These bits here belong to the network. These bits here belong to the host, to you, to your end node, to there's many different names for it. But so this 1 here actually belongs on this side. So your address is 192.168.129 is the whole thing, .103. But 128, this bit belongs to the network, and then a bit over here belongs in this direction. So you can have, now I could have all these bits here belong to the same network. It's the 128 network. So I could have an address with these three here. So this is 1, 2, 4. So that is 7. So I could have 128 plus 7. Plus 7. And of course that gives us 15 and 3, and so it would actually be 192, 168, 135 dot, and we could have the same thing, 103, and that would be on the same network as 192, 168, 129.103, and it's two different addresses, but it's on the same network. Now I know this is overly complex. It has nothing to do with the electronics we're doing. It's just bonus material. Now, something that does have to do with the electronics we're doing is what is next. So let's do, in simplest terms, if you keep 255, 255, 255 dot 0, then it divides along the octets, and it's easier to understand. Because then 129, if all the octets were there, would be part of your network. But anyways, I just thought I'd mention that since, this is some of the things I do for a living. And this is where I have a bleed over between electronics and network engineering. So let's do new. Don't save that. Okay, Larry had a question about testing. Okay, guys. Larry had a question about testing transistors. And there is a way to test transistors. And I'm actually going to be referring to a book that you will see down in the show notes about how to test almost everything electronic, 3rd edition, Dalton T. Horn is the book I'm referring to for how to test almost everything. And I decided to do this. We're not going to be testing a lot of stuff until we understand it better. We're going to be implementing it in our projects before we start actually testing things. But I decided to answer this question just because I had the answer to it anyways. Now, I myself, when I test an NPN or a PNP, there are multimeters that have PNP and NPN transistor testers right on them. And they do everything that we're going to describe right here. And they do it much quicker and much more easily than we are going to do it here. And generally speaking, you want to test this component outside of the circuit anyways. You don't want to test it in your circuit. So you're going to wind up putting it into a breadboard, and then you've got to test. I'll show you. There's actually 6 different tests you have to do. But the vast majority of transistors are standard bipolar of the bipolar variety. Bipolar means that the semiconductor contains 2 PN junctions. What is a PN junction? Now, like I said, don't worry if you're not getting this. This is a little more advanced stuff that we're not gonna. If we were creating our own transistors, we'd need to understand this a little more. But you need to understand it for testing. And of course, this is what a PN junction is. I'm not going to read this to you. You can look it up, or you can hit pause and you'll see it for yourself. But functionally, the bipolar transistor can be considered a pair of back-to-back diodes interconnected. So for our testing purposes, we could think of them as back-to-back diodes. What does that mean? Well, first let's do our NPN and our PNP. So, wow, that is just horrible. So we got N, P, N, and this is similar to what you're going to see in that book below. Of course, this is where I learned it, so Not surprised. P and P. So here we've got the base, we've got the emitter, and we've got the collector. And here we have the base, we have the emitter, I'm sorry, it's the same thing. Collector, emitter. We just put it in differently. So that's the emitter. And so basically the way this looks is, if you remember our diagrams of a diode, looks like that, right? And then another diode looks like that. Now you can't build a transistor using diodes, so that's not what I'm doing here. So we've got base, and then we have our collector and our emitter. And I'm not telling you whether this is a PNP or an NPN. Look at the direction of the diodes, and look at the flow of electricity, and look at the collector and the emitter, and if you need to go review it in one of the previous tutorials, then review it. I think it's good practice for you anyways. So you can test the diodes easily with an ohms meter. You simply measure the resistance from one lead to another, then reverse the leads and measure the resistance again. So you got to be like measuring from here to here, here to here, or actually the 6 points that you measure are emitter to base, base to emitter, so emitter to base, base to emitter, so you reverse it, and I'll show you what I mean by that in a minute. Base to emitter, emitter to collector, collector to base, and base to collector. Wait a minute, I'm missing one here. Emitter to base, base to emitter, emitter to collector, collector to emitter. Sorry about that. So here, the flip side is collector to emitter. And the last one is base to collector. So like, for instance, take base to collector. We do collector to base and then base to collector. What does that mean? Well, when you have your ohms meter, and you have your plus and your minus and your little meter here, and you have these guys running out, and this is how the diode looks. What you're doing is you're measuring one side. Like when you're measuring in this direction of the diode, then you will get on your ohms meter. We're measuring in ohms. And the diode going in the opposite direction. What a bad diode. Bad diode. We'll just color that in. Now, if you're measuring him in positive here, and then common or negative. So you measure it in one direction, then you measure it in the other direction. And basically you can take a known good one and see what all your measurements are going to be. And then if any of these are incorrect reading on any of these measurements, indicates that the transistor is bad and it should be replaced. So you should measure a very high resistance in one direction and a low to moderate resistance in the other direction, depending on how you're measuring. But basically, how I do and I don't go through all this. First of all, PNPs and NPNs are relatively inexpensive. It's a lot harder to measure these components when it's actually in a circuit, so you run into some problems. But if you're testing anything, I highly recommend, you'll see it below. It is how to test almost everything just in case, if you're watching this, if you're not watching this on Vimeo and you've got an embed somewhere, like Wonder How To or something, you may not see the notes down below. And it's this book I'm using is the third edition, and it's by Dalton T. Horn. Like I mentioned to Larry, I responded to his email, and I said, I don't know everything. And I especially don't know everything all the time. So I heavily rely on my library for almost everything, from programming to electronics. If I'm looking to do something, I'm constantly looking stuff up. I don't have everything memorized. And so don't worry yourself if you don't have everything memorized. But you should be building a library. And I've been recommending some books. This is another one. If you want to test things, how to test almost everything electronic, this is a good book to add to your library. And that's about it. So anyways, when you're just to mention again, you have a test lead here and a test lead here, and then you'd reverse it and you do the opposite, and you should have an opposite reading. Same thing, here to here, and you reverse it, you should have an opposite reading. Here to here, you reverse it, you should have an opposite reading. It's low resistance in one direction, high resistance in another direction. And you just use your ohms meter. And that's how you test a NPN and a PNP to see whether they're good or bad. So put it in your breadboard and use your leads. Not on your multimeter, but connect your leads to alligator clips, and then from alligator clips to those nice wires that we use on our breadboards. And you can do this testing. Basically, if my PNP or NPN isn't working in my breadboarded circuit, I try another one. And if that's not working, then I look at the way I've built my circuit. And I actually have a multimeter that I can stick them into, and it does all this testing for me and tells me whether it's good or bad. And it does it almost instantaneously. Okay, guys, I don't know what the next video is going to be. I think we might build a... it's one of two things. I think we're going to build a 5-volt regulator, a 5-volt voltage regulator, so we could stick 9 volts, 12 volts, DC, and have it come out a straight 5 volts. So I think it's very simple. It's just 4 capacitors and a 5-volt regulator. I think that's going to be our next, because I need to actually build one of those for a project I'm working on. I'm working on a sonic walking stick for the blind, and that's going to be part of our tutorials too. I'm going to open source it all. I'm using open source hardware, and I'm going to open source all the code so anybody can build this as well. But to start with, like I mentioned, I'm using one of those Arduinos that I've got to supply power for. It doesn't have a power regulator in it. So we're actually going to build, I think we'll build a power regulator next. And then the tutorial after that, I think we will do relays. Because we've learned how to control a little LED with our light sensor. But let's control something AC. And of course, when I do that video, I'm going to tell you don't do this, because working with AC is dangerous. But I'm going to do it, and I'm going to recommend that you don't do it, but I'm going to show you how you can do it. Just so you know. So you could take this, because these microcontrollers that we use, they only supply, these digital pins only supply like 20 milliamps. So the basics, the only thing you're going to do is control either LEDs, or you control something else that controls LEDs, either an NPN or a PNP or a relay. So I think that's going to be our next 2 videos, and I think I'll work on one of those next weekend. Maybe I can get both of them done in a weekend. We'll see. But anyways, I hope you guys are enjoying the videos, and I'll see you for the next one.